Hello, today we're going to dive into a powerful application of calculus, curve sketching. By the end of this lesson, you will be able to use derivatives to accurately sketch the graph of a function. Our main goal is to learn how to sketch curves using derivatives. We'll achieve this by following a systematic, step-by-step process. This process will help us identify all the key features of a function's graph. Here are the steps we'll cover. First, we'll find the domain and intercepts. Second, we'll find the first derivative to analyze increase, decrease, and local extrema. Third, we'll find the second derivative to analyze concavity and inflection points. Finally, we'll put it all together to sketch the graph. Let's get started with our first step. Our first objective is to find the domain and intercepts of a function. These are the most basic features of any graph. First, let's find the domain. The domain is the set of all possible input values, or x values, for which the function is defined. For most polynomial functions, the domain is all real numbers. However, you need to be careful with functions that have denominators, like rational functions, or even roots, like square roots. For example, if you have a function with a denominator, you must exclude any x values that make the denominator 0. If you have a square root, the expression inside the root must be greater than or equal to 0. Next, we find the intercepts. These are the points where the graph crosses the x-axis or the y-axis. To find the y-intercept, you set x equal to 0 and solve for y. This gives you the point, 0, f of 0. To find the x-intercepts, you set y equal to 0 and solve for x. This means you're finding the roots of the equation f of x equals 0. Let's see this in action with our first example. Let's work through our first example. We'll sketch the curve of the function f of x equals x cubed minus 3 x squared plus 2. Our function is f of x equals x cubed minus 3 x squared plus 2. First, let's find the domain. Since this is a polynomial function, there are no denominators or even roots. Therefore, the domain is all real numbers. The domain is all real numbers, which we can write as negative infinity to positive infinity. Next, let's find the intercept. First, the y-intercept. To find the y-intercept, we set x equal to 0. F of 0 equals 0 cubed minus 3 times 0 squared plus 2, which simplifies to 2. So the y-intercept is the point, 0, 2. Now for the x-intercepts. This is where we set the function equal to 0. We need to solve the equation x cubed minus 3x squared plus 2 equals 0. This is a cubic equation, which can be tricky to solve. We can try to find integer roots using the rational root theorem. Let's test x equals 1. Plugging in 1, we get 1 minus 3 plus 2, which equals 0. So x equals 1 is a root. This means x minus 1 is a factor of the polynomial. We can use polynomial division to find the other factor. Dividing x cubed minus 3 x squared plus 2 by x minus 1 gives us x squared minus 2 x minus 2. So our equation becomes x minus 1 times x squared minus 2 x minus 2 equals 0. The quadratic factor doesn't factor nicely, so we use the quadratic formula. Using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, we get x equals 1 plus or minus the square root of 3. So our x-intercepts are at x equals 1 plus the square root of 3, and x equals 1 minus the square root of 3. We've now completed the first step. We have the domain and all the intercepts. Now for the second step, using the first derivative. Our objective here is to find where the function is increasing or decreasing and to locate any local maxima or minima. We'll use the first derivative, f prime of x, to find intervals of increase and decrease, and to classify local extrema. First, we need to find the critical points. Critical points are the x values where the first derivative is either 0 or undefined. These are the only places where a function can change from increasing to decreasing, or vice versa. For a polynomial, the derivative is always defined, so we just need to find where it's 0. Once we have the critical points, we can use them to divide the number line into intervals. Then, we test a point in each interval to see if the derivative is positive or negative. If the derivative is positive in an interval, the function is increasing. If it's negative, the function is decreasing. This is the first derivative test. This test also helps us classify local extrema. If the derivative changes from positive to negative at a critical point, we have a local maximum. If it changes from negative to positive, we have a local minimum. If the sign doesn't change, it's neither. Let's apply this to our example. Let's continue with our example. F of x equals x cubed minus 3x squared plus 2. We'll now find the first derivative. Using the power rule, the derivative of x cubed is 3x squared, and the derivative of negative 3x squared is negative 6x. The derivative of 2 is 0. So f prime of x equals 3x squared minus 6x. Now let's find the critical points by setting the derivative equal to 0. We set 3x squared minus 6x equal to 0. We can factor out 3x, which gives us 3x times the quantity x minus 2 equals 0. This equation is true if 3x equals 0, which means x equals 0, or if x minus 2 equals 0, which means x equals 2. Our critical points are x equals 0 and x equals 2. Now we use these critical points to create a sign chart for the first derivative. We place our critical points, 0 and 2, on a number line. This divides the line into 3 intervals: negative infinity to 0, 0 to 2, and 2 to infinity. Let's test a value in each interval. For the first interval, let's test x equals negative 1. F prime of negative 1 is 3 times negative 1 squared minus 6 times negative 1, which is 3 plus 6, or 9. Since 9 is positive, the function is increasing on the interval from negative infinity to 0. For the second interval, let's test x equals 1. F prime of 1 is 3 times 1 squared minus 6 times 1, which is 3 minus 6, or negative 3. Since negative 3 is negative, the function is decreasing on the interval from 0 to 2. And for the third interval, let's test x equals 3. F prime of 3 is 3 times 3 squared minus 6 times 3, which is 27 minus 18, or 9. Since 9 is positive, the function is increasing on the interval from 2 to infinity. Now we can classify our critical points. At x equals 0, the derivative changes from positive to negative. This means we have a local maximum. The y value is f of 0, which we found earlier to be 2. So there's a local maximum at the point 0, 2. At x equals 2, the derivative changes from negative to positive. This means we have a local minimum. The y value is f of 2, which is 2 cubed minus 3 times 2 squared plus 2, or 8 minus 12 plus 2, which equals negative 2. So there's a local minimum at the point 2, minus 2. We've now successfully used the first derivative to find where the function is increasing and decreasing, and to locate its local extrema. Let's move on to our third step, using the second derivative. Our objective here is to find where the function is concave up or concave down, and to locate any inflection points. We'll use the second derivative, f double prime of x, to find intervals of concavity and inflection points. First, we need to find the possible inflection points. These are the x values, where the second derivative is either 0 or undefined. These are the only places where a function can change its concavity. For a polynomial, the second derivative is always defined, so we just need to find where it's 0. Once we have these points, we can use them to divide the number line into intervals. Then, we test a point in each interval to see if the second derivative is positive or negative. If the second derivative is positive in an interval, the function is concave up, meaning it looks like a cup. If it's negative, the function is concave down, meaning it looks like a frown. An inflection point is a point where the concavity actually changes. So if the second derivative changes sign at a possible inflection point, then that point is a true inflection point. The second derivative also provides an alternative way to classify local extrema, called the second derivative test. If the second derivative is positive at a critical point, it's a local minimum. If it's negative, it's a local maximum. If it's 0, the test is inconclusive, and you must use the first derivative test. Let's apply this to our example. Let's continue with our example, f of x equals x cubed minus 3x squared plus 2. We'll now find the second derivative. We start with our first derivative, f prime of x equals 3x squared minus 6x. The second derivative, f double prime of x, is the derivative of the first derivative. Using the power rule again, we get 6x minus 6. Now, let's find the possible inflection points by setting the second derivative equal to 0. We set 6x minus 6 equal to 0. Adding 6 to both sides gives 6x equals 6, so x equals 1. This is our only possible inflection point. Let's use this point to create a sign chart for the second derivative. We place our point, 1, on a number line. This divides the line into two intervals, negative infinity to 1 and 1 to infinity. Let's test a value in each interval. For the first interval, let's test x equals 0. F double prime of 0 is 6 times 0 minus 6, which is negative 6. Since it's negative, the function is concave down on the interval from negative infinity to 1. For the second interval, let's test x equals 2. F double prime of 2 is 6 times 2 minus 6, which is 12 minus 6, or 6. Since it's positive, the function is concave up on the interval from 1 to infinity. Since the concavity changes at x equals 1, this is a true inflection point. Let's find its coordinates. The y value is f of 1, which is 1 cubed minus 3 times 1 squared plus 2, or 1 minus 3 plus 2, which equals 0. So the inflection point is at 1, 0. Notice this is also one of our x-intercepts. We can also use the second derivative test to confirm our local extrema. Remember, our critical points were x equals 0 and x equals 2. At x equals 0, f double prime of 0 is negative 6. Since it's negative, we have a local maximum, which matches our first derivative test result. At x equals 2, f double prime of 2 is 6. Since it's positive, we have a local minimum, which also matches. The second derivative test confirms our findings. We have now analyzed the concavity and found the inflection point. We're ready to sketch the graph. We've gathered all the information we need. Now for the final step, sketching the graph. Our objective is to combine all our findings into a single, accurate sketch. We'll use all the points and intervals we found to create the graph. Let's summarize our key findings for f of x equals x cubed minus 3x squared plus 2. We have a y-intercept at 0, 2, x-intercepts at 1, 0, and approximately 2.730 and minus 0.730. We have a local maximum at 0, 2, a local minimum at 2 minus 2, and an inflection point at 1, 0. The function increases, then decreases, then increases again. It's concave down, then concave up. Let's plot our key points first. We plot the y-intercept at 0, 2, the local minimum at 2, minus 2, and the inflection point at 1, 0. Now, let's connect the dots, keeping the concavity and increase/decrease in mind. From negative infinity to x equals 1, the graph is concave down. From x equals 1 to infinity, it's concave up. Starting from the left, the graph is increasing and concave down until it reaches the local maximum at 0, 2. Then it starts decreasing, still concave down, until it hits the inflection point at 1, 0. At this point, the concavity changes to concave up. The graph continues decreasing, now concave up, until it reaches the local minimum at 2, minus 2. Finally, it increases and remains concave up as x goes to infinity. And there you have it, a complete sketch of the function f of x equals x cubed minus 3x squared plus 2, built entirely from its derivatives. We have successfully combined all the information to create an accurate graph. Let's try a second example. This time, we'll sketch the curve of a rational function, f of x equals x squared over x squared minus 1. Our function is f of x equals x squared over x squared minus 1. First, the domain. Since this is a rational function, the denominator cannot be 0. We set x squared minus 1 equal to 0, which gives us x equals plus or minus 1. So the domain is all real numbers except for 1 and negative 1. These points of discontinuity, x equals 1 and x equals negative 1, are vertical asymptotes. This is a key feature of rational functions. We have vertical asymptotes at x equals 1 and x equals negative 1. Next, the intercepts. For the y-intercept, we set x equals 0. F of 0 is 0 over negative 1, which is 0, so the y-intercept is at the origin, 0, 0. For the x-intercepts, we set the function equal to 0. A fraction is 0 only if its numerator is 0. So we set x squared equal to 0, which gives us x equals 0. The only x-intercept is also at the origin, 0, 0. Finally, let's check for horizontal asymptotes. We do this by taking the limit as x approaches infinity. The limit of x squared over x squared minus 1 as x approaches infinity is 1. This means we have a horizontal asymptote at y equals 1. We've now completed the first step for this rational function. We have the domain, vertical asymptotes, intercepts, and a horizontal asymptote. Now for the second step of our second example, finding the first derivative of f of x equals x squared over x squared minus 1. We use the quotient rule, which states that the derivative of u over v is v times u prime minus u times versus prime all over v squared. Here, u is x squared, so u prime is 2x. And v is x squared minus 1, so v prime is 2x. Plugging these into the quotient rule, we get x squared minus 1 times 2x minus x squared times 2x all over x squared minus 1 squared. Now let's simplify the numerator. Distributing the 2x gives 2x cubed minus 2x minus 2x cubed. The 2x cubed terms cancel out, leaving us with negative 2x. So the first derivative is negative 2x over x squared minus 1 squared. Now, let's find the critical points by setting the derivative equal to 0 or finding where it's undefined. The derivative is undefined at x equals plus or minus 1, but these are asymptotes, not critical points. The derivative is 0 when the numerator is 0, which is when negative 2x equals 0 or x equals 0. So our only critical point is x equals 0. Let's create a sign chart for the first derivative. We need to include our critical point and our asymptotes. We place negative 1, 0, and 1 on the number line. This creates 4 intervals. Let's test a value in each interval. Notice that the denominator, x squared minus 1 squared, is always positive. So the sign of the derivative is determined solely by the numerator, negative 2x. In the first interval, negative 2x is positive, so the function is increasing. In the second, it's positive, so it's increasing. In the third, it's negative, so it's decreasing. And in the fourth, it's negative, so it's decreasing. Now let's classify our critical point at x equals 0. The derivative changes from positive to negative. This means we have a local maximum at x equals 0. The y value is f of 0, which is 0. So there's a local maximum at the origin, 0, 0. We've now analyzed the increase, decrease, and local extrema for this function. Now for the third step of our second example, finding the second derivative of f of x equals x squared over x squared minus 1. We start with our first derivative, f prime of x equals negative 2x over x squared minus 1 squared. We'll use the quotient rule again. Here, u is negative 2x, so u prime is negative 2. And v is x squared minus 1 squared. We need the chain rule to find v prime. V prime is 2 times an x squared minus 1 times 2x, which simplifies to 4x times x squared minus 1. Plugging these into the quotient rule, we get x squared minus 1 squared times negative 2 minus negative 2x times 4x times x squared minus 1 all over x squared minus 1 to the fourth power. This looks complicated, but we can simplify it. Notice that x squared minus 1 is a common factor in the numerator. We can factor out x squared minus 1 from the numerator. This allows us to cancel one of the factors in the denominator, simplifying the expression to negative 2 times x squared minus 1 plus 8x squared all over x squared minus 1 cubed. So our second derivative is f double prime of x equals 6x squared plus 2 over x squared minus 1 cubed. Now let's find the possible inflection points by setting the second derivative equal to 0 or finding where it's undefined. The numerator 6x squared plus 2 is always positive, so the second derivative is never 0. It's undefined at x equals plus or minus 1, but these are asymptotes. This means there are no inflection points. Let's create a sign chart for the second derivative. We only need to include our asymptotes. we place -1 and 1 on the number line. This creates 3 intervals. Let's test a value in each interval. Remember, the numerator is always positive, so the sign is determined by the denominator, x squared minus 1 cubed. In the first interval, the denominator is negative, so the function is concave down. In the second, it's negative, so it's concave down. In the third, it's positive, so it's concave up. We've now analyzed the concavity. Let's use the second derivative test to confirm our local maximum at x equals 0. f of a prime of 0 is 2 over -1, which is -2. Since it's negative, we have a local maximum, which confirms our previous finding. We have now analyzed the concavity and confirmed our local extremum. We're ready to sketch the graph. We've gathered all the information for our second example. Now for the final step, sketching the graph of f of x equals x squared over x squared minus 1. We'll use all the points and intervals we found to create the graph. Let's summarize our key findings. We have vertical asymptotes at x equals plus or minus 1, a horizontal asymptote at y equals 1, and a local maximum at the origin, 0, 0. The function is increasing on the intervals -∞ to -1 and -1 to 0. It's decreasing on 0 to 1 and 1 to infinity. It's concave down on -∞ to 1 and concave up on 1 to infinity. Let's start by drawing our asymptotes. We draw vertical dash lines at x equals -1 and x equals 1, and a horizontal dash line at y equals 1. Now, let's plot our local maximum at the origin, 0, 0. We place a point at the origin. Let's sketch the graph in the middle section, between the vertical asymptotes. We know it's concave down and has a local maximum at 0, 0. The graph increases from the asymptote at x equals -1, reaches its peak at 0, 0, and then decreases towards the asymptote at x equals 1. It's a smooth, concave down curve. Now for the left section, where x is less than -1. We know the function is increasing and concave down, and approaches the horizontal asymptote y equals 1. The graph comes from the horizontal asymptote, y equals 1, increases, and then shoots down towards the vertical asymptote, x equals -1. Finally, for the right section, where x is greater than 1. We know the function is decreasing and concave up, and also approaches the horizontal asymptote, y equals 1. The graph comes from the vertical asymptote, x equals 1, decreases, and then approaches the horizontal asymptote, y equals 1 from above. And there you have it. The complete sketch of the rational function f of x equals x squared over x squared minus 1. We've successfully used derivatives and asymptotes to create an accurate graph. Let's try one more example. This time, we'll sketch the curve of a function with a root, f of x equals x times the square root of x plus 3. Our function is f of x equals x times the square root of x plus 3. First, the domain. The expression inside the square root must be non-negative. We set x plus 3 greater than or equal to 0, which means x must be greater than or equal to -3. So the domain is the interval from -3 to infinity. Next, the intercepts. For the y-intercept, we set x equals 0. f of 0 is 0 times the square root of 3, which is 0. So the y-intercept is at the origin, 0, 0. For the x-intercepts, we set the function equal to 0. We have x times the square root of x plus 3 equals 0. This is true if x equals 0, or if the square root of x plus 3 equals 0, which means x equals -3. So our x-intercepts are at 0, 0, and -3, 0. We've now completed the first step for this function. We have the domain and all the intercepts. Now for the second step of our third example, finding the first derivative of f of x equals x times the square root of x plus 3. We'll use the product rule, which states that the derivative of u times v is u prime v plus uv prime. Here, u is x, so u prime is 1, and v is x plus 3 to the 1/2 power. Using the chain rule, v prime is 1/2 times x plus 3 to the -1/2 power. Plugging these into the product rule, we get 1 times the square root of x plus 3 plus x times 1 over 2 times the square root of x plus 3. To find critical points, it's helpful to combine this into a single fraction. We find a common denominator, which is 2 times the square root of x plus 3. This gives us 2 times x plus 3 plus x, all over the common denominator. Simplifying the numerator, we get 3x plus 6, so f prime of x equals 3x plus 6 over 2 times the square root of x plus 3. Now, let's find the critical points by setting the derivative equal to 0, or finding where it's undefined. The derivative is 0 when the numerator is 0, which is when 3x plus 6 equals 0, or x equals negative 2. The derivative is undefined when the denominator is 0, which is when x equals negative 3. So our critical points are x equals negative 2 and x equals negative 3. Let's create a sign chart for the first derivative. We only need to consider the domain, which starts at negative 3. We place our critical points, negative 3 and negative 2, on a number line. This creates 2 intervals within our domain. Let's test a value in each interval. For the first interval, let's test x equals negative 2.5. f prime of negative 2.5 is negative 1.5 over a positive number, which is negative. So the function is decreasing on the interval from negative 3 to negative 2. For the second interval, let's test x equals 0. f prime of 0 is 6 over 2 times the square root of 3, which is positive. So the function is increasing on the interval from negative 2 to infinity. Now let's classify our critical points. At x equals negative 2, the derivative changes from negative to positive. This means we have a local minimum at x equals negative 2. The y value is f of negative 2, which is negative 2. So there's a local minimum at the point, minus 2, minus 2. At x equals negative 3, the derivative is undefined. This is an endpoint of our domain. Since the function is decreasing as we approach this point from the right, it represents a local maximum. The y value is f of negative 3, which is 0. So there's a local maximum at the point, minus 3, 0. We've now analyzed the increase, decrease, and local extrema for this function. Now for the third step of our third example, finding the second derivative of f of x equals x times the square root of x plus 3. We start with our first derivative, f prime of x equals 3x plus 6 over 2 times the square root of x plus 3. We'll use the quotient rule again. Here u is 3, x plus 6, so u prime is 3, and v is 2 times x plus 3 to the 1/2 power. Using the chain rule, v prime is 2 times 1/2 times x plus 3 to the negative 1/2 power, which simplifies to 1 over the square root of x plus 3. Plugging these into the quotient rule, we get 2 times the square root of x plus 3 times 3 minus 3x plus 6 times 1 over the square root of x plus 3 all over 4 times x plus 3. To simplify, we can multiply the numerator and denominator by the square root of x plus 3. This clears the fraction in the numerator. We get 6 times x plus 3 minus 3x plus 6 all over 4 times x plus 3 to the 3/2 power. Simplifying the numerator gives 3x plus 12. So f double prime of x equals 3x plus 12 over 4 times x plus 3 to the 3/2 power. Now let's find the possible inflection points by setting the second derivative equal to 0, or finding where it's undefined. The derivative is 0 when the numerator is 0, which is when 3x plus 12 equals 0, or x equals negative 4. However, this is outside our domain of x greater than or equal to negative 3. The derivative is undefined at x equals negative 3, which is an endpoint. This means there are no inflection points. Let's create a sign chart for the second derivative. We only need to consider the domain, which starts at negative 3. We place negative 3 on the number line. This creates one interval within our domain. Let's test a value in this interval, say x equals 0. F double prime of 0 is 12 over 4 times the square root of 27, which is positive. So the function is concave up on its entire domain, from negative 3 to infinity. We can also use the second derivative test to confirm our local minimum at x equals negative 2. F double prime of negative 2 is 6 over 4, which is positive. Since it's positive, we have a local minimum, which confirms our previous finding. We have now analyzed the concavity and confirmed our local extremum. We're ready to sketch the graph. We've gathered all the information for our third example. Now for the final step, sketching the graph of f of x equals x times the square root of x plus 3. We'll use all the points and intervals we found to create the graph. Let's summarize our key findings. The domain is x greater than or equal to negative 3. we have a local maximum at the endpoint, -3, 0, and a local minimum at -2, -2. The function is decreasing from -3 to -2, and increasing from -2 to infinity. It is concave up on its entire domain. Let's plot our key points first. We plot the local maximum at -3, 0, and the local minimum at -2, -2. Now let's connect the dots, keeping the concavity and increase/decrease in mind. The graph starts at the local maximum, -3, 0, and is concave up. From -3, 0, the graph decreases, staying concave up until it reaches the local minimum at -2, -2. From there, it increases, still concave up, and continues to increase as x goes to infinity. And there you have it, the complete sketch of the function f of x equals x times the square root of x plus 3. We've successfully used derivatives to create an accurate graph, even for a function with a restricted domain. Now it's your turn to practice. Here are 2 problems for you to work on. Pause the video and try to sketch the curves using the steps we've learned. The first function is f of x equals x to the 4th minus 4x cubed. The second is f of x equals 1 over x squared plus 1. Remember the steps. Find the domain and intercepts. Find the first derivative for increase/decrease and local extrema. Find the second derivative for concavity and inflection points, and then sketch the graph. Good luck. Welcome back. Let's go through the solution for the first practice problem. F of x equals x to the 4th minus 4x cubed. Here's the solution for f of x equals x to the 4th minus 4x cubed. First, the domain is all real numbers. The y-intercept is at 0, 0. The x-intercepts are at 0, 0, and 4, 0. Domain is all real numbers. Intercepts are at 0, 0, and 4, 0. Next, the first derivative, f prime of x equals 4x cubed minus 12x squared. The critical points are at x equals 0 and x equals 3. The first derivative is 4x cubed minus 12x squared. Critical points are at x equals 0 and x equals 3. The sign chart for the first derivative shows the function is decreasing on -infinity to 3 and increasing on 3 to infinity. At x equals 0, the derivative doesn't change sign, so it's not an extremum. At x equals 3, it changes from negative to positive, so we have a local minimum. The function is decreasing on -infinity to 3 and increasing on 3 to infinity. There is a local minimum at 3 minus 27. Now, the second derivative, f double prime of x equals 12x squared minus 24x. The possible inflection points are at x equals 0 and x equals 2. The second derivative is 12x squared minus 24x. Possible inflection points are at x equals 0 and x equals 2. The sign chart for the second derivative shows the function is concave up on -infinity to 0 and 2 to infinity, and concave down on 0 to 2. Since the concavity changes at both x equals 0 and x equals 2, they are both inflection points. The function is concave up on -infinity to 0 and 2 to infinity, and concave down on 0 to 2. There are inflection points at 0, 0, and 2 minus 16. Finally, we sketch the graph using all this information. It starts concave up and decreasing, passes through the inflection point 0, 0, becomes concave down and continues decreasing, passes through the inflection point 2 minus 16, becomes concave up and continues decreasing until the local minimum at 3 minus 27, and then increases, staying concave up. Here is the final sketch of the graph. Let's go through the solution for the second practice problem. F of x equals 1 over x squared plus 1. Here is the solution for f of x equals 1 over x squared plus 1. First, the domain is all real numbers since the denominator is never 0. The y-intercept is at 0, 1. There are no x-intercepts. There is a horizontal asymptote at y equals 0. Domain is all real numbers. The y-intercept is at 0, 1. There are no x-intercepts. There is a horizontal asymptote at y equals 0. Next, the first derivative. F prime of x equals negative 2x over x squared plus 1 squared. The only critical point is at x equals 0. The first derivative is negative 2x over x squared plus 1 squared. The only critical point is at x equals 0. The sign chart for the first derivative shows the function is increasing on negative infinity to 0 and decreasing on 0 to infinity. At x equals 0, it changes from positive to negative, so we have a local maximum. The function is increasing on negative infinity to 0 and decreasing on 0 to infinity. There is a local maximum at 0, 1. Now, the second derivative. F double prime of x equals 6x squared minus 2 over x squared plus 1 cubed. The possible inflection points are at x equals plus or minus 1 over the square root of 3. The second derivative is 6x squared minus 2 over x squared plus 1 cubed. Possible inflection points are at x equals plus or minus 1 over the square root of 3. The sign chart for the second derivative shows the function is concave up on negative infinity to negative 1 over root 3 and 1 over root 3 to infinity, and concave down on negative 1 over root 3 to 1 over root 3. Since the concavity changes at both points, they are both inflection points. The function is concave up on the outer intervals and concave down in the middle. There are inflection points at approximately plus or minus 0.58. Finally, we sketch the graph. It approaches the horizontal asymptote y equals 0 from the left, increases and is concave up, passes through the inflection point, becomes concave down, reaches the local maximum at 0, 1, becomes concave down again, passes through the second inflection point, becomes concave up, and then decreases towards the horizontal asymptote y equals 0. Here is the final sketch of the graph. Let's quickly recap what we've learned today. We've seen how to use a systematic process to sketch the graph of a function. We started by finding the domain and intercepts. Then, we used the first derivative to find critical points, intervals of increase and decrease, and local extrema. After that, we used the second derivative to find possible inflection points, intervals of concavity, and actual inflection points. Finally, we combined all this information to create an accurate sketch. This process is a powerful tool that allows you to understand the behavior of a function and visualize its graph without needing to plot hundreds of points. It's a fundamental skill in calculus. Thank you for watching, and keep practicing.